Hi, I'm Troy McClure. Wait, no, I'm Sam Ryan. You might remember me from hit shows such as Studying the Galactic Sausage and Sausageology, A Tale of Two Sausages, and also this deranged shirt. It's beautiful. It's fashion. I know what you're thinking. You're not Simon, and that's correct. No, I do not have a PhD, and I also do not have a plastic crack addiction, though those two things are very close to becoming true. No, Simon is on paternity leave, and so has asked me to create a video worthy of Mordor, and that is what I'm going to do. Today, I'm going to talk to you about some exciting recent developments in the field of exoplanets. I'm a current fourth year at the Institute of Astronomy in the University of Cambridge at St. Catherine's College, studying galactic archaeology, and you might be asking, what does the history of the Milky Way and its dynamics have to do with exoplanets? It has nothing really, and I don't study exoplanets. I actually don't know anything about exoplanets. So I've got three amazing academics who will do that job for me. Starting in the past with Lord Martin Rees, the Astronomer Royal, one of my third year mates, talking about the recent discovery of K2-18b, finishing with Professor Jerry Gilmore on how Gaia, the best satellite ever, will be revolutionising the detection of exoplanets. So I first asked Martin Rees, how did we get to where exoplanet science is today?
I'm Martin Rees, and we're talking in the Astronomy Institute of Cambridge. I've been a member for a long time and was director of the institute until I retired. I do remember that, and it was a very exciting result, of course. And in the next 10 years, we had lots more exoplanets, and so it became clear that most stars in the sky had retinues of orbiting planets, just like the Sun has the Earth and the other familiar planets, and this makes the night sky far more interesting. And then, of course, this raised high on the agenda the question of, could there be any life out there? In the case of all new discoveries, you start off with just a few puzzling objects and maybe rather crude observations. People focus on those particular objects and things eventually firm up. The understanding is very crude, and that develops a bit. And I think over the years I've written some of the early papers on trying to make sense of some of those strange animals in the cosmic zoo, as it were, found by X-ray astronomers and by radio astronomers and by the big optical telescopes. The kind of work I did was based on very simple models where you can think they're spherical or smooth, etc. What's been a huge boost to astronomy has been the ability to do computer simulations, and it's for that reason that we can now study how gas with magnetic fields orbits around black holes and swirls into them, and understand the way in which our universe evolved from its fairly smooth beginnings to the present universe dominated by galaxies in clusters. It's a great triumph, but still the data is limited, and to actually get an image of a Earth-like planet is going to be difficult, but that's the challenge.
So I'm standing here in Neville's Court in Trinity College in Cambridge, where a couple hundred years ago a certain Isaac Newton discovered the speed of sound by just clapping his hands. Even though it has nothing to do with exoplanets, I just thought it was neat. That was the past though, and well, we're now in the present. So I was joined by fellow third year Mons who worked on the recent discovery of K2-18b.
My name is Måns Holmberg. I'm a third year PhD student here at the Institute of Astronomy. I do exoplanet atmospheres, specifically data analysis. We only look at transiting planets. So if you have your star and your planet goes in front of it, and some of the starlight is passing through the atmosphere. So then we take observations throughout the whole thing when it passes in front of the star. And then essentially we have only the starlight when the planet is not transiting, and when the planet is transiting, we can take the difference of those two. And that spectrum has imprinted spectral features which tell us what atomic and molecular species are in the atmosphere. So with the new James Webb Space Telescope, we've been able to probe atmospheres of exoplanets to much higher precision. So now when we can shrink down those errors, we can really start to see the features of the spectrum in much more clarity. We found the first evidence of photochemistry on a hot Jupiter. That was sulfur dioxide was found in the atmosphere, and the only way you can produce that is through photochemistry. I think it was predicted to be there, but no one really expected it. They found a bump which they couldn't explain initially. Then they had to add the molecule, and then it matches. So that was a new unexpected discovery. More recently, the K2-18b spectra, where we found methane and carbon dioxide for the first time in a planet in the habitable zone. It was an international team led by Nico Madusaran here in Cambridge. I've done the data analysis, or as part of a team, we've done the data analysis, taking the raw data that comes from the telescope when it beams down the ones and zeros, and then processing the data, trying to figure out like how much flux actually hit the detector, and then how that produce a spectrum that you can then compare to these models. Where we took 2 observations with 2 different instruments of K2-18b, and this has been proposed to be a possible Haitian world. And here Haitian means a mini Neptune with a possible liquid water ocean and a hydrogen layer on top, an atmosphere. We saw big spectral features right away. They could be seen by eye. You didn't have to run a retrieval, essentially. I mean, we did. But just the fact that you can see the features so clearly, which wasn't possible before. People thought that was water, but in reality, with our more accurate observations over a broader wavelength range, showed that those features were actually due to methane. So when we look at the distribution of planets that we have found so far, the most common type of planet lies somewhere between Earth in size and Neptune. And we don't really have an analog of that in the solar system. So Haitian was a candidate planet type that was proposed to maybe be some of these planets in between here. So we found methane and carbon dioxide. Then there was another tentative sign of dimethyl sulfide, which on Earth is only produced by life. However, we need more observations to really confirm these findings. There's upcoming observations of I think 4 or more Haitian candidate worlds. So JWST, through these observations, have shown that it is capable to do these sort of discoveries. So I think we're just in the beginning of what is to come.
I'm here on the Backs in Cambridge, known to many hit films such as The Theory of Everything, and also Simon and Sam on a cam, on the cam. And I've still not tried punting since that fateful day. But we've just heard from Mons about carbon dioxide, methane, and potential biosignatures. I'm next joined by Professor Jerry Gilmore, one of the main PIs for the Gaia mission, a satellite built by the European Space Agency with a goal to understand history and structure of the Milky Way. And so far it's revolutionised galactic archaeology with the first 3 data releases, but with the 4th and 5th coming out between 2025 and 2030, with the field of exoplanets experience a kind of Copernican revolution. And so I asked Jerry, exactly how will Gaia do this?
I'm Jerry Gilmore. I'm Professor of Experimental Philosophy here at the Institute of Astronomy in Cambridge. My field of research is the local universe, everything from nearby stars and their chemical elements right through to where the Milky Way came from. The main thing in which I've been involved for the last few decades is the Gaia spacecraft, the ESA mission. I was one of the original mini 5 people who proposed it, and I was on the original team that worked with industry to design it into its current magnificent state. It's the first ever large-scale space astrometry mission. So that means it measures very accurately the position of stars at a given time. By then repeating those measurements as Gaia and the Earth together go around the Sun, you see the stars from different angles, and that gives you a parallax measure in the same way that our eyes give you a distance measure. You then keep repeating that over time, and you see not only the parallax, i.e. how far away the star is, which is the reflex Earth motion, but you also see the proper motion of the star. So you get a 5-dimensional image of how the star is moving through the Milky Way, and then you can complement that with a radial velocity, a spectrum. Gaia does all the bright stars itself, which gives you the 6th dimension, the line of sight. So then you get instantaneously the 3-dimensional position of a star and its motion in each of those 3 dimensions. And so you can see how it is moving around and see how the Milky Way works. Gaia was launched just before Christmas 2013, so it's nearly 10 years now. It was originally designed to measure 1 billion stars. It was called the Billion Star Surveyor. In fact, it's done a little more than 1.8 billion.
Oh, wow.
It's produced about 8,000 papers. The feature of Gaia is that the data is so huge and so complicated that only about the first third of it's been published so far, and so it's only the first 3.5 years. Now, if you want to go looking for exoplanets, you have to look for a few years to see the effect, apart from hot Jupiters or something where things are happening on a timescale of a day. Gaia is still operating. It's got about another 18 months before it runs out of fuel. And over its lifetime, it will have been operating for about 11 years. And so over that 11-year time, it's going to be fantastic for exoplanets. Even the next data release, which is still only going to be the first half of the data, the first 5 years or 5.5 years, will be fantastic. But it's probable that perhaps 20,000 planetary systems will be mapped out by Gaia. But for real detailed microscopic stuff, the number will probably be less than 1,000. We can say, here is a Neptune of this particular mass in this particular period, and here is a Uranus, and so on. But the key thing is that Gaia will find these systems, and then by then we will have things like the Extremely Large Telescope with its ultra-high precision planetary camera. We're going to take pictures of the stuff, and so you can go and look, say, does this planet go white in winter and green in summer, that sort of thing. The next really big data set, which is the full time series, not been released yet, so everybody can go out then and look and fit their own models to every object and say what sort of planets are hiding here or whatever. That will come out at probably the end of 25, so that will be DR4, but that will still only be the first half of the data. So the second full data release, the full and final one, and every single data point, which will be hundreds of trillions of data points, that will probably be about 2030, because it'll take another 5 years after the end of the mission just to do all the computer processing, because the data volumes are just huge, and so it just takes time to grind them all through and do everything. Unlike most experiments where the people who are the science team, the project team, do the basic analysis of their data and they publish the basic important results. Gaia, a few sample results are put out, which are really just educational. They're designed to show the community how to analyse the data. The real exciting thing about Gaia is that it's a genuine open science machine. It's the first ever open science machine in which all the data are just given freely to the whole world. And the whole world gets to do the exciting first science.
It's a brave new world, something remarkable, exhilarating, that we're standing on a precipice of something generally amazing. There's not much after the future, you can't go past the future, so there's not much left in this video. I'm going to hand it over to myself, who will be somewhere else in Cambridge. I'm standing outside the Cambridge observatories, which is not just one building, there are many observatories all around us, but this is the observatory, this is OBS. And this was where emeritus people such as Einstein and Eddington sat in that very spot. The bench has now disappeared, but there used to be a bench there. Talked about Eddington's discovery of light bending around the sun. And in that discussion, they changed our understanding of relativity and of the universe. Obviously, this is what this video has done to you. It has changed your perception of exoplanets. I think there's only one thing left, which is some words of encouragement and wisdom from Martin himself.
Well, I would extol it as a stimulating subject, which does provide a good research career for many people. In order to pursue that career, then of course you need a fairly broad scientific background. You need to understand some mathematics and physics, certainly a lot of computing, but now perhaps in biology as well, or complex chemistry. So there's a wide variety of inputs that we're going to need to have if you want to try and interpret what's being found. Plus, of course, all the variety of technologies. And there's lots of excitement and lots of variety. It's going to be a subject where the ratio of problems to people is going to remain gratifyingly high. So you can find your own problem and there won't be too much duplication, etc. And so that's very good. And I think the other feature which is attractive about the subject is that it is something which attracts a far wider interest among amateurs and the general public. And I think that's a boost. I think it's nice to know that there's a public interest. If I'm sitting next to someone on a train or on a plane, then if I want to have a conversation, I should say, I'm an astronomer, and that will almost certainly the first question will be, are we alone? And then you can go from there. Whereas if I want to be alone, I just say, I'm a mathematician, and I have to shut them up.
Those were some truly wise words from Martin there. Anyway, I hope you all enjoyed this video, this exploration into past, present and future exoplanet research. It's only left for me to say thank you very much, Simon, for giving me this opportunity to speak to the wider world. Many people would not give me this opportunity if they have seen all the memes, all the terrible, no, I'm not going to say that. Well, if you're starting your undergrad about now, by the time you do your PhD, God help you, you'll be getting there with Gaia DR4 and discovering all the new exoplanets. You can find me over on Twitch every so often, where I do some study streams, some game streams, a podcasty talk show stream, and you can find me over there at samwise2450. And also remember to like, comment and subscribe. It's a goodbye from me. Goodbye.